and thanks to the organizers for the opportunity to be here and to speak. It's one of my first international conferences, and it's just amazing being in this environment full of people with really incredible ideas to share, and there's so much to do over here. And on a personal note, this is where my mother's side of my family comes from, Scotland, so it's my first chance to sort of repatriate in a sense by proxy for her or something. Anyway, it's good to be here is the point. I'd also like to thank the New Zealand Mathematical Society, who's given me some support to be here as well. So today I'll be talking about groupoids of non-finitely aligned high rank graphs. And I thought I'd start with a little bit of history, but I see that I can probably be light in how much I say here, because toward the end of the day, we're going to have a much more comprehensive survey of high rank graph literature, I'm sure, from David. And also because this has been reviewed in more depth than me already in this conference. So I'll just try and highlight the things that are relevant. So directed graphs were first used by Enomoto, Fuji, and Watani to model C-star algebras. And the groupoid model came along by Kumjin, Pasgraben, and Renault in 1997. And that was for row finite graphs. So perhaps already my convention is clear. I'm thinking of worrying about when I've got infinitely many edges going into a vertex. So in the row finite case, we've got a graph groupoid model in 1997, and that was the beginning of the graph groupoid models. And by 2002, 5 years later, Patterson had fully generalized the groupoid model so that any graph is permitted. So that full generality was achieved in those 5 years, removing any finiteness conditions. And then came high rank graphs. So the definition, I think, was motivated by work Robertson and Steger were doing in 1999. And they were defined by Kumjin and Pask in the year 2000, and graph groupoids were given for them in the row finite no sources case. So the clock has started again. Let's see how quickly we can get to no finiteness conditions, but still a groupoid model. So finitely aligned graph C-star algebras were attained by Rabin, Sims, and Yent in 2004, but there isn't a groupoid model in there yet. And then work by Farthing, Muley, and Yent a year later achieved this groupoid model for finitely aligned graphs. So 5 years later, we've got this graph groupoid model, but it's for the finitely aligned case. So the finiteness condition is still there, and you might look at this as a loose end to some degree. It feels kind of like not, I don't want to say unsatisfying, because that feels like it devalues the work that's been done. And as we've heard from Victoria's talk, the finitely aligned condition, going back to Hausen, is really quite a weak condition. It doesn't give you much to work with. But it feels like we still need to complete this program of removing finiteness conditions and still attaining the groupoid model that we expect or that we want. And I put Diokin and Renault groupoid in quotation marks here, because of course in the non-finitely aligned setting, as we heard from Jack the other day, we do have an approach to associating a groupoid in their C-star algebras to non-finitely aligned higher rank graphs, since any higher rank graph is going to be left cancelled at a small category. But we're interested to see what we can do in the specific setting of higher rank graphs, trying to push the Diokin and Renault style groupoid that has been throughout the literature before. So that's kind of the challenge today that I want to look at. How can we build a groupoid that's kind of like a Diokin and Renault groupoid, but not exactly, for a non-finitely aligned high rank graph? And so it's good to learn what we can from history. And I saw in the introduction to Patterson's paper in 2002, when he attains the groupoid model for generality for directed graphs, he says how one of the key challenges is that the usual space of paths that's going to be the unit space for your groupoid that you try to write down can fail to be locally compact. And the approach to that is to throw in some finite paths that occur in a certain sort of way in order to give you that local compactness. And we find this too, that in the higher rank graph setting, when we try and say no finite alignment, we're going to meet a similar lack of local compactness. And we'll have that same approach of, I've got my infinite paths and I'll throw in some finite paths to try and do what's worked in the past. But what we're going to find is that actually we've thrown too many and we're going to have to throw some out again. So let's get technical. Higher rank graph, as we've seen defined earlier in this workshop, you've got a small category and you've got a function which measures how long the elements of the category are. And it gives you this factorization property, unique factorization property, which is quite strong, saying if I can divide the length of a path into 2 bits, then I can uniquely divide the path itself into bits of those lengths. And just for a bit of notation, we can look at, so I'm talking about K graphs. So n to the K is the range of lengths that paths may take. And I can look at coordinate-wise maxima if I look at two lengths. So the join of M and N in this way. And I might want to point out all of the paths of length N, which I'm going to denote lambda N. And I think Jack called them, or maybe because I can't remember where the terminology was first used, but we look at these principal right ideals carefully as well in order to describe our finite alignment condition.
Do you include 0 in your naturals?
Yes. So the 0 will be necessary so that vertices, sorry.
You should.
As you should. Oh, well, careful. Everybody stay seated. The 0 is going to be necessary for our purposes, at least, because we want our vertices to have length 0. Yeah. So finite alignment, one of the many things that I've learned just being here in this conference is that perhaps this condition goes back further to the work of Hausen in the 50s, in essence, though not in exactly the same setting. Is that we say lambda, our higher rank graph, is finitely aligned. If anytime I pick 2 paths in the graph, their common extensions are sort of finitely generated. Okay, yeah. And so just to say where I've come from in this project, the first thing that I've ever really done in the graph world is constructing a groupoid from a non-finitely aligned higher rank graph. And so I think probably compared to many in the room, I sort of come at things from a different angle, whereas everybody else is kind of was maybe there for the creation of graph algebras, and so is used to a traditional approach to the graph groupoid. I started from the other direction, and so to me it feels like when you add finitely aligned back in, the world's your oyster, which is not to say I can do anything I like obviously it's still a very difficult setting to work in, but I've for a long time been floundering trying to do just the basic things in the non-finitely aligned setting. So it feels like the world's your oyster. And then maybe you can relate to this feeling where sometimes you go, I've just got to look this thing up. I've never really understood, why do we say the world's your oyster? So you go on Wikipedia and you go, oh yeah, it's because of the thing about you might find a pearl in your oyster. It's like, I've never found a pearl in an oyster. I'm not sure about you. But for that reason, they represent luck. And then I thought, oh, we're going to be in Scotland, and so maybe I should find an analog to that. And I'm told by the internet that white heather is the local symbol of luck. So the world's our white heather, where we have finitely aligned friends. Yeah, I hope so. So anyway, I need to progress. I haven't, wait, what time do I have until? 10:25, 10:35. Oh, thank goodness. Okay. So the goal today is to start with a graph. It's not necessarily finitely aligned, and we want to get to a kind of Diacono-Renault groupoid. It's not going to exactly be that, but that's going to first take building a locally compact Hausdorff space. And as we saw from Patterson's remark in his paper in 2002, that first step of getting the right unit space can be quite challenging. And once we've got a nice space, we're going to try and act on that space in the usual sort of way, by shifting bits off of your paths. And if we can act nicely on that space, or if we can act in the bare minimum sensible way on that space, then we'll write down what the Diacono groupoid is going to be. And so I've got this diagram trying to picture how I view an element of a Diacono groupoid. You've got a triple XQY that we've seen many times before. And I was thinking, how do you just sort of say this in plain English? I guess you say something like coincide eventually. But then I realized, oh no, I'm suddenly doing the Northern convention, which is like blasphemy where I come from, because coincide eventually would be like if I'd drawn the arrows going this way. So if I was a true Southern convention person, which I feel like I am, but then I realized I wasn't, I had to say something like the paths coincided forever until recently. So there's pros and cons. Okay, so we're trying to build a locally compact Hausdorff space. To do that, we're going to use a filter approach. So in the K-graph world, I think the first approach is to think of some canonical K-graphs that are built on into the K in a certain way, and you look at morphisms into the graph that you're looking at, or the other way around, no, into the graph that you're looking at, to describe what the paths should be. But this corresponds to looking at certain subsets of lambda with respect to the natural partial order on it. And these are exactly the non-empty hereditary directed sets that Jack was talking about the other day, going back to Nika's work in 1992, which I'm calling filters, and that's just because the same definition seems to work in so many different contexts if you just are willing to turn your partial order or pre-order in a different direction. And so it kind of seems like the terminology filter can just generalize across these different things. But anyway, the point is a filter is going to be a nice subset of your graph where anytime you've got a path in that, anytime you've got an element in that set, all of its initial segments are contained in the set too. That's to say it's hereditary. And it's directed, meaning anytime I have two paths in the set, I can find at least one common extension of them. And I wanted to say something about why should we look at filters. As I said before, you can write down the definition of a filter easily whenever you have a binary relation on a set, right? So you could write that down, and then there's the question, is this a good reflection somehow of the structure that's actually happening in my structure? And I think one of the key things to highlight in that regard is that one of the nice properties of filters is that the degree map is injective when you restrict to any particular filter you look at, any filter you like. So in any filter, a subset of your graph, there is at most one thing of any particular degree. And I think this also kind of speaks to the idea that our filters, our paths, should kind of go out into the graph in some way. Like they can't just enumerate the things of any particular degree. They kind of have to be not sparse, but broad through the graph or something like that.
So you sort of, the image under D is a filter in NK.
Yes, yeah, that's right. It will be. Yep. And so we want to turn this into a topological space. And as I said, the issue is how do I make sure this is going to be locally compact Hausdorff, especially in the non-finitely aligned setting, it's easy for compactness to fail. And so our approach to begin with is like, we're going to hold on for dear life to any kind of compactness we can find. So our filters as a collection, that's a subset of the power set of lambda. It's just some subsets. So I'm going to endow the power set of lambda with the product topology where each 0, 1 is discrete. And this is what Nika does in his paper in 1992 as well, when he's looking at a sort of special case where the graph he's looking at nice submonoids of groups, and he does this kind of thing. And that's going to be a compact Hausdorff space And so I've got the collection of filters inside of a compact Hausdorff space, and I'm just going to try and draw on the compactness that's ambient as much as possible. But things quickly go wrong. So as Trent Yeens showed his paper on topological higher rank graphs in 2007, you can construct graphs that demonstrate the filters will be not locally compact under this topology. So I'm going to do that. I'm going to present Trent Yeens' graph, one of the two that he demonstrates. And I think of it kind of as an infinitely infinite book. What do I mean by that? So here we have what we call a one skeleton of a higher rank graph, where my dashed edge is one color and the solid edge is another color. And this itself is a higher rank graph, but it's not a particularly interesting one. So this graph I'm going to think of as the spine of the first book that I'm building. So just imagine physically that you're trying to build a book and you've got a spine. And I guess this is not the way that people build books. You probably start with pages and then put a spine on it, but I'm going to start with the spine.
Sorry, Malcolm, when you talk about colors, these are the different colors in the graph correspond to the different copies of n when
Yes.
you go through the degree map. Okay.
Yes, yeah, that's exactly right. So maybe I would think of mu as having the degree 1, 0, and lambda as having the degree 0, 1, and the vertices having degree 0, 0.
The other way around.
Up to us. What you prefer. Okay, so we've got a spine of a book, mu lambda, and then I'm going to put one page into the book so far. So I've got beta 1 and I've got alpha 1. And as Jack was saying, you have to be really careful about your identifications when you're trying to write down k-graphs. So the first step we have to make sure of is that we've still got a sensible k-graph obeying unique factorization. And to do that, I'm going to say that the path beta 1 lambda has to be equal to the path alpha 1 lambda, because the path beta 1 mu cumulatively has degree 1, 1, and I could write that as 0, 1 plus 1, 0, or as 1, 0 plus 0, 1. So it's this notion of I have to be able to do a dashed solid thing as a solid dashed thing as well, and these need to be the same thing. So we have identifications happening, but the point is you put the first page in your book, mu lambda is the spine. Well, I could just do that infinitely, and that's my first infinite book. I could just actually chuck in infinitely many pages. And so imagine if you're opening the book and you're flicking through the pages, your thumb's on the U's and you're going through all of the pages. So that's the first infinite book. Already it's non-finitely aligned because I do the same identifications for all of the copies for all of the pages. And so mu lambda they not only have infinitely many common extensions, but there's no finite generators of those infinitely many common extensions. They're all distinct from each other. So let's level up. Where's the infinitely infinite book? So take that infinite book that you just built and then make infinitely many copies of them and then stick them all together again at lambda, and lambda becomes the new spine. So this is your infinitely infinite book where you've got your lambda as the spine, and you can flick through to any particular mu I, and then there you can flick through infinitely to any particular u I k as well. So I've got this massive book, and it's here where we find a lack of local compactness. Maybe I'll skip the details, but you get the vibe that I've got a lot of infiniteness going on. And so I try to find a compact space around lambda, but I can't. That's the point. So we need a new idea because the filters are not going to form a locally compact space. So the idea is to be sneaky and just go straight for the boundary path space, because the boundary path space is constructed as a closure of another space. So you go, well, maybe I get a closed space inside of a compact space, maybe things will start working. So we need a notion of infinite paths, because really we've just been looking at the sort of finite paths so far, or all paths. We're going to call a filter an ultrafilter if it's maximal with respect to inclusion. And I'll denote the set of ultrafilters by curly U. And I'll take the closure of the ultrafilters within the power set. So this is kind of the usual strategy. You say, I'm looking at my ultra filter, I'm looking at my infinite paths, and I take the closure. But it's perhaps unusual to take the closure within the power set. Usually you take it within the filters, but that's not going to work for us because, as we saw before, the filters already is not a nice topological space. So we take the closure inside of the power set, but the power set being compact Hausdorff tells us that the closure of the ultra filters is going to be compact. It's closed inside of a compact space. But then that's kind of suspicious because we know even in the one graph setting, your unit space shouldn't always be compact. So we got compactness, but we kind of want less than that. So maybe a small observation as well. Since I was taking the closure inside of the whole power set, I have to be careful about where the empty set is living. This is something that Renaud and Williams do in the paper in 2017. When they're working in p-graphs, they're quite careful about where the empty set lives. If and only if your category has infinitely many vertices, you're going to get the empty set jumping into the limit of the ultra filters as well. So that singleton of the empty set is a nice closed set. So I'm going to remove that from my compact space and I get a locally compact Hausdorff space. So it kind of feels like, okay, maybe we're in business. We've got a locally compact Hausdorff space for any non-finitely aligned higher rank graph. So that was the first step, and now step 2, we need to act on that. Okay. So how are we going to do that? Well, let's look at a simpler non-finitely aligned graph. Remember the first infinite book you built, and then there were all of those U's. And now imagine someone annoying has come along and glued the other end of your book together. So now you can't open the book at all. They're kind of fixed at both ends, but like there are infinitely many pages in there, but it's just glued on both ends. So we collapse it down like that. We've got another non-finitely aligned graph, but it produces some pretty strange looking paths in our new path space, because each beta n mu is going to generate an ultra filter. And now I've got a sequence of ultra filters, and because of the way that the topology we have that we inherit from the product topology on 0, 1 to the lambda, if I take the sequence of ultra filters b and mu, it's just going to converge to mu. But that's on one side of the equation. Since we've got all these identifications happening, beta n mu was really always an alpha n lambda, so I get the lambda jumping in at the same time. So that sequence of ultra filters converges to this set v lambda mu, that bottom corner, the spine of the book. But that's not directed. Lambda and mu don't have a common extension, so it's not a filter anymore. So this closure of the ultra filters gives us non-filters to play with. And that's a pretty wacky notion of a path. You know, it feels like maybe it shouldn't be there. And indeed, it doesn't do the things we need it to do. Lambda's in this path, and so I should be able to shift lambda off and put it back on and be where I started, but that doesn't happen. If I shift lambda off, I just get to the vertex W. So if I put lambda back on, I'm just going to get lambda. I lost mu along the way. So it's just hard to do the basic things in these non-finitely aligned graphs. So maybe if I do 2 naive things, it will make a clever thing. You know, do 2 wrongs make a right? I don't know. Let's see. So since I really want filters, because I can take things off and put them back on filters really nicely, I'm just going to naively demand that I only have filters, right? I take my closure of the ultra filters, I throw out the empty set, and then I throw out any non-filters that I gained along the way. But F was the filters, they weren't a nice space to begin with. They're neither open nor closed in certain examples in the power set of lambda. So intersecting with them is not going to give me a nice space. So here comes the second naive thing. Well, I'm going to take the interior of those things. I'm going to take the interior of this intersection of the closure of the ultra filters that are really filters. So I've just got so I think it's kind of nice because the method is to say I'm going to take the closure of my infinite parts, and then you're kind of taking the interior of that again, once you've restricted to filters. So there's kind of this back and forth of I'm going to throw some things in and I'm going to throw some things out. And that gives us a locally compact Hausdorff space because it's open in a nice space, and it's actionable. I can act on it and retrieve things invertibly locally.
So actionable, you mean it's invariant?
I don't mean it technically. I guess by that I mean my shift on and shift off maps satisfy formulae like if I shift off and then shift back on, I'm where I started. And if I shift on and I shift off, then I'm where I started. That's kind of the basic thing. And there's some topology happening there too, as well. But yeah, so actionable in a very minimal sense, just to get the definition of the groupoid making sense, really.
If you do half of it, like shift off, what's left is still within the set.
So that is exactly one of the problems. That's one of the many things that we have to be suspicious about is this in this construction. So that's why I'm saying it's a Diacono-Renault style groupoid, because when we act, if I shift something off, we can construct examples where you're actually no longer in this boundary path space. And that's really one of the key issues that makes it hard to check anything about the groupoid that we construct. So yeah, that's a good point. So you might say, well, that's a whole lot of mucking about with the space. That's not very pretty. At least if you're only concerned about the finitely aligned case, this is exactly the same as say, taking the closure of the ultrafilters inside of the filters. So it retrieves the normal thing. It reduces to the same finitely aligned structure. And I'm going to call this partial lambda the boundary path space. Maybe I already did. Okay, so step 3, we got a locally compact space in step 1, then we were able to act on it very minimally, not minimally, we were able to act on it in some bare minimum way. And that's just enough to write down the definition of a groupoid that could make sense. And it follows the same scheme as various other Diacono-Renault groupoids, but it just kind of avoids the technology of I've actually got an action on a locally compact Hausdorff space and just kind of writes down what the groupoid elements should be. And with this, you can check that for any K-graph, non-finitely aligned potentially, this groupoid is going to be a Hausdorff topological groupoid, and its unit space is locally compact Hausdorff. But when I say topological groupoid, I just mean operations are continuous. Again, we get the bare minimum out so far. It remains to be seen whether it actually fails to be étale and everything you would want in the general setting. I haven't written down an example yet, but there's reason to believe more changes have to be made. But at least so far, what we have in the finitely aligned setting reduces to an ample étale locally compact Hausdorff groupoid like you would expect out of the graph groupoids. With that said, there's already a distinction to be made. The groupoid we've constructed in the general setting is always going to be Hausdorff, whereas Jack's presented in his groupoid construction for non-finitely aligned left cancellative small categories. He has examples of K-graphs that are non-finitely aligned where the groupoid is non-Hausdorff. So already we know that this groupoid would be different to Jack's groupoid, even in the K-graph setting. So there's something interesting happening here, or different happening here. I won't praise myself too much. So what progress have we made in this way? For the examples that Trent Yen presents in that paper in 2007, where he says that first of all, it's hard to write down a locally compact Hausdorff space, and second of all, it's hard to get operations in the groupoid being continuous. We do have a way of doing it that will reduce nicely to the finitely aligned case. And actually, our construction works verbatim for any submonoid P of a group. So I've expressed it so far today in K-graph world that if you replace n to the K with any submonoid of a group, it doesn't have to be conical, it doesn't have to be quasi-lattice ordered or any of that. Then we have this theorem as well. So in particular, you could let the graph just be a group by itself, and this groupoid is going to coincide with the group. It retrieves the group. So what's next? Remove finitely aligned completely, actually, because it's not very satisfying to many of the people in the room, I'm guessing, to just have a topological groupoid. It's like, oh, come on, what am I supposed to do with that? And then worry about these suspicious things that have been popping up. Not only that our action on the space isn't really an action, because you can exit the space just by acting on something. And then there's other strange things, like we can write down examples where when we took the interior, we actually threw out some ultrafilters. which are meant to mimic infinite paths. So somehow that's behaving very differently to what we get in the finitely aligned setting, where infinite paths are always there. So, and then what I'm unsure about so far, do I even know that the boundary path space is going to be non-empty for any graph you give me? I haven't been able to write down a graph where it is empty yet, but it feels like maybe I could make, you know, an infinite book or something, and then it would be, I'm not sure. And that's all I have to say, so thank you.